Okay, our next speaker is Luciane Quoos from Universidad Federal de Rio de Janeiro, Brazil. She is going to talk about rational functions with a small value set. Whenever you are ready, Luciane. Luciane.
Yeah, okay, sorry, that was my turn without microphone. Huh? Okay. So yeah, I'd like to thank you for organizing the session, for Melina and Maria Char and Erivelto, and also for the invitation to talk here. So this is a joint work with my friends, Daniele Bartoli and Erivelto Borges. Bartoli from Perugia, Italy, Universidade de Perugia, and Erivelto Borges from USP, São Paulo. Okay. So, oh, sorry. Oh, what? Oh, it's okay. It's not changing the page. I don't know. Okay. So, well, I'll start giving a definition, what we mean about value set rings. So if you take any polynomial over a finite field of degree d, so what is the value set is just you think f as a function over fq, and so you just compute f of alpha for alpha in fq. Okay, so this is the value set of the function. It's just the image. Okay. So, well, since you have a polynomial of degree d, then you have that the pre-image of any alpha in FQ, this has at most d elements, because you are looking to the zeros of a polynomial of degree d in a field. So we always have this very simple bounds that the cardinality of the value set is at least q over d, and at most q because you are inside over fq. So this is for polynomials, okay? And well, we say that the polynomial f is a minimal value set polynomial if the lower bound is, and well, these minimal value set polynomials have been studied by Carlitz, Mills, and Gomes-Calderon in the 60s and 70s. So you have many results there. There are some there is a nice result from Carlitz or Mills that relates the condition of a polynomial being a minimal value set and the derivative of the polynomial. It gives you a condition. And more recently, and 2013, Borges and Conceição have worked again on minimal value set polynomials, and they provide many families. For example, families like if you have a polynomial over fq to the n, and you want the value set of the polynomial being a subfield of your field. Okay, so they have many families over there. And really recently, we have a work from Volok and Sparlinski, where they study the value set of sparse polynomials. Okay? So we have so the cardinality of the value set is between these two numbers. And if the value set of a polynomial is q, then it's called a permutation polynomial. And this has been widely studied. Now we have many papers on permutation polynomials. So one question we could wonder ourselves is which values between q over d and q can be, which numbers between q over d and q are the cardinality of a certain value set for certain polynomial f. Okay. So we have worked not with polynomials, but with rational functions. Okay. So if I give you a rational function, so a rational function can have poles. So it's natural when you want to think about the value set of rational functions, you should include the infinite. Okay, so we start with a rational function of degree d. So the degree of a rational function is just the maximum value between the degree of the numerator and the denominator. And the value set of the rational function h is just h alpha for alpha in P1 now. Okay, so, and this is in P1 also. And again, our rational function has degree d, so you have this lower bound for the value set of h, q plus 1 over d, and it can be at most q plus 1. Okay, and then generalizing the idea for polynomials, we say that the rational function h is a minimal value set rational function if you have the lower bound at x. Okay, so these are the functions we are going to study. Well, so first thing is, if you take f a minimal value set, then you can think a minimal value set polynomial. You can think a polynomial always as a rational function too. So you can think about the value set of the polynomial as a rational function, okay? So it fixes infinite. So for example, if you take f a minimal value set polynomial of degree d, then as a rational function, it's easy to see that the number of, the size of its value set is q plus 1 over d if d divides q, and the q plus 1 over d plus 1 otherwise. It means that in the case that d divides q, so your polynomial seen as a rational function is again a minimal value set rational function. And for the other cases, you don't have that it's a minimal value set rational function. Okay, so we can do some natural questions like do minimal value set rational functions of degree d, where d does not divide q, exist? Can we characterize them? Because we already know that if d divides, it's a minimal value set rational function. What happens if d doesn't divide? Okay, so this is one question. Second natural question is, can we characterize rational functions for which the minimal value set is really q plus 1 over d? So it's minimal, or it's just a minimal plus 1, or more generally, we could say like the size of the value set is small. So I'm going to say what we mean about small later on. Okay. So at first, we will give a relation between value sets and algebraic curves. So take a rational function h equal to f over g. So we always suppose that f and g are coprime, okay? And we denote the value set of h by alpha 1, alpha r. Okay, so we have r elements. And then we can associate the algebraic curve that is given by when you do hx equal to hi. You want to know when x and y have the same value. Okay, so you get this curve, fx times gy minus fy, gx equal to 0. And now we call S the number of affine rational points on the curve. Okay, so are the points over fq and affine. So we start noticing that if I give you any rational any element in fq, okay, that's in the value set alpha I equal to h of y0, so it's going to be of this way. And if I give you x0 any other element in fq, so we have that x0 is also in the pre-image of alpha I. It means that h of x0 is equal to h of y0 if and only if the point P, x0, y0 is in the curve. So we relate elements in FQ have the same image with these elements giving a point on your algebraic curve. Okay? So let NI denote the pre-image of any guy in the value set. Okay? Then, for sure, since you are evaluating everyone in FQ, you have that the sum of the pre-images is just Q plus 1, okay, because you're evaluating FQ plus infinite. And you also have that, from this observation up here, we just have that the sum of the square of Ni is just the number of FQ rational points on your curve. Okay? And from this, we can conclude that the number of affine rational points on your curve has to be larger or equal than Q squared over R. So what can we say about this? It means that if the value set is small, I mean, if R is small, your curve has many points. Okay, but curves with many points, they cannot be irreducible, and this is the way we are going to go on. So what we have is that the value set is small if and only if your curve has many points. But as I said, you have Hasse-Weil theorem that says if you have projective curve absolutely reducible. So if it's absolutely reducible, okay, of genus G, you have that the number of rational points over FQ is smaller than Q plus 1 plus 2G square root of Q. What this means? This means that if your curve has many points, it should be a reducible curve. You should be able to factor it. Okay, so, So suppose your curve, CH has degree D and is absolutely reducible. Okay, then the number S of rational points can be at most this number given by the Hasse-Weil, and this has to be smaller than Q plus 1, D minus 1, D minus 2, square root of Q. Okay, because G is smaller than D minus 1, D minus 2 over 2. So you have this upper bound for S. So resuming, for H, a rational function of a small degree, okay, if you have a small value set, the size of the value set is small, the curve has many points, and if the number of points pass this number, your curve should have reducible factors, okay? Oh, sorry, here is not irreducible. Okay, it should factor. So this is one connection, okay? So if you have a small rational function with a small value set, the curve should factors. There is a second connection that is like H being a minimal value set rational function, and this extension being a Galois extension. Okay, so this observation, it first came from examples, actually. So how does it happen? So if you take H, any subgroup of the automorphism group of the rational function field, so this group is just the PGL to Q. Okay, so these are rational functions of degree 1. And if you look to the fixed field by H, then this is just Galois theory. Then this gives us an extension of degree D, and the minimal polynomial of X over this field is just you do T minus sigma I of X for I from 1 to D. These are the guys, and you get your polynomial that lives in is defined over FQ of Ajax for some polynomial Ajax. Okay, and you can prove this. If you start, now we start with a rational function such that this is a Galois extension. So we know that this is a Galois extension. And then we have the subgroup here. Okay. So we have the subgroup, and well, such that this is the subgroup that gives you the Galois extension. For this case, the value set of your rational function is at most the minimum value plus 1, q plus 1 over d plus 1. And we know when we have equality here. Okay? We have equality if and only if the action of the group on P1 has at least 2 short orbits. Remember that this number is always larger than q plus 1 over d. Okay? So if you have a Galois extension, you have this. How you prove that? The idea here is not too hard. You analyze the action of H in the pre-image of the value set. But the pre-image of the value set is just P1. So when H acts on P1, you have certain orbits. So you suppose you have a certain number of orbits, and you apply Riemann-Hurwitz formula for this extension. You can show that you can have at most 3 orbits, and then you analyze the cases. So that's more or less the idea to prove this. Okay, so Galois extension of this shape always gives you small value sets. And we are gonna see that, well, the opposite is almost always true. Okay. So I wanna say something about, well, the curve CH in general first. So giving H a subgroup of PGL2Q of this shape, we can associate the following polynomial in 2 variables. Okay, so I give you this, I put a polynomial like this, huh? Cy, I use the denominator here, and the numerator appears here. Okay, so giving a subgroup, I have this algebraic curve. And now we are gonna see a connection. So we have a theorem that says the following. Take any 2 polynomials, f and g, okay, and consider this algebraic curve, f of y, g of x, minus fx, g of y. This is the curve we had in the beginning. Okay. Now you look to the irreducible factors of g that have of this type. I mean, we are considering the irreducible factors that are conics or lines. You just look to lines and conics. And then something very nice happens. Well, the very nice thing that can be proved is that if you look to the set H that is given by sigma I of t, AIT plus B here, over CIT plus di, like here, like we had in the beginning. Okay, so this set is a subgroup of automorphism of K of t. So, okay, so you have your curve of that shape, you collect your irreducible factors that are conics and lines, and you can associate for these irreducible factors a certain set that is actually a group. So that's a very nice thing. And you can also show that the curve gh of x constructing this way up here is always a factor of this curve, gx of y. Okay. So you know that so for example, so if your curve here, gx of y, if all its irreducible factors are conics and lines, so actually these 2 polynomials has to be the same. Okay. So this is what we use actually for the general results. So what we can show is that, well, if I give you a rational function h equal to f over g, has a small value set, and also the degree of your rational function is small, then this extension has to be a Galois extension. So what we mean, like for having a small degree and over G. So okay, so F and G are co-prime. Okay, we are supposing that the degree of G is D larger than 2. And the degree of F is D minus S. Okay, so the degree of a rational function is like on the denominator. Okay, so you are saying that infinity goes to 0 in your function. Okay, then we give a limitation on the degree. So if 3D minus 2S is smaller than this number, so for example, if Q is large, okay, you have more possibilities for D and S. Okay, so if the degree is small like this, and the size of your value set is smaller than, remember this part is the lower bound. Okay, so it's the lower bound plus something. So like if this something is larger than 1, you have something nice. You can show that this is a Galois extension of degree D. Okay. So I'll give you just an idea, okay, how you do that. So the idea is that you look to the algebraic curve. Okay, remember that a small value set for us, intuitively, this curve should have a lot of, should factors a lot over FQ. And so if you give it the curve, fx gy minus fy gx, okay, associated to this rational function, so this has degree 2D minus S, because G had degree D and F had degree D minus S. So this is a curve of degree 2D minus S. So, well, so from the conditions on the degree of H and the size, so this is possible, actually, well, it's a lot of work. We can prove that this curve factors in the irreducible components, okay? And from a second theorem that I skipped, actually we can prove that, okay, it factors in the reducible components, and all these reducible components, they are lines or conics. So actually it factors in S lines and D minus S conics. Okay, so it factors on this, and now we can use the theorem we had proved before. Okay, so if you just have the conics and lines, we know that we can get a group collecting this line and conics. So suppose that these are all your irreducible factors. Okay, HI from I equal to 1 from D. So you have here lines and conics. So from the other theorem, we have that this set is a subgroup of automorphism of the rational function field. This is a subgroup of PGL to Q. Okay. And from another theorem, we can prove out then that this actually FQ of X over FQ of H is Galois. Okay. This group will give you the fixed field for the function H. You started everything. It glued things. Okay, we know that this is going to be a Galois extension, but a Galois extension given by the function here h, where h is the function you started. Okay. So this is the idea. Okay. So, well, actually, this is all I had to say. And for sure, we have like open problems here. For example, we know that the extension is Galois, but a question I'd like to ask, for example, can we characterize the extensions of this shape fqx over fqh that are Galois? I mean, can we characterize polynomials, rational functions h, such the extension rational extension fq of x over fq of h is a Galois extension? Can we characterize these polynomials? If you could characterize, we could give explicit minimum value set rational functions. Okay. So, well, gracias por la atención.
Thank you very much, Luciana.
Hey, nice to see you, Eve.
Can I have a question, Melina?
Yes, of course, Daniel.
Luciane, very nice, very nice. Very nice, you know, connections and, you know, and results. I was thinking your last theorem, the one in page 10, could you be able to say something about just above minimal, right? Because we know that when you are not permutation, there is a gap, yeah, there is a jump, and then come all the values down to the smallest size, the minimal value set, right? That you are working. So would it be possible with this theorem there somehow to characterize the next value above the minimal value and maybe construct some cases?
Yeah, that should be something nice to be done. But actually, Daniel, it depends if this number is positive or not. No, the second part here, no, because you see this part here depends on Q, on D. So, well, you should to choose probably D and S. But yeah, you should look at it for sure. You should look at these very carefully, you know, and then I could say something like.
No.
But it depends.
Yeah, I'm not saying that it will be immediate.
Yeah, it depends on three parameters, no, Q, D, and S. So.
Yes, but precisely because you have three parameters, you may be able to play a bit and then find some particular case, you know, very close to the minimal value. I mean, the minimal values, as you know, and you cited there are far less results.
Yeah, but you see that the minimal value has to be at least this value plus 2, because plus 1 I showed you before that you have that once that give you. So we have this number, you have this number plus 1. So you need actually this guy to be larger than 2.
Right.
This will be the next one to see if you can get this plus 2.
Yeah, you need to play, but I think it will be nice if you can add a result like that. I think will be nice. Yeah. Anyway, nice work. Thank you.
Thank you.
Are there any other questions? Thank you very much, Luciane. It was a very nice talk. Thank you.